To remind ourselves of this fact, let's put f of x equal to 1 for x equals a, and 0 for x greater than a and less than or equal to b. Then if we look at the so-called inner product of f with respect to L2, we get the integral from a to b of modulus of f of x squared, and that's the integral from a to b of 0, as we saw in our video on norms. And why is that? Because f is piecewise continuous on the interval a to b, and for all but finitely many points in the interval a to b, f is equal to 0. So the integral of f squared, for that matter, over a to b just agrees with the integral of 0 over a to b, which is of course 0. Now let's suppose that we are in the happy position of having an inner product on a vector space X, any vector space that you like over the complex plane, and let's define a new quantity. Let's put the norm of f will be the square root of inner product of f with f. Then this map is indeed a norm on X. In particular, we know that the inner product of f with f is always non-negative, so we can always take the square root of this non-negative real number. And we call this the norm induced by the inner product. So whenever I talk in the notes or in an exercise about a norm in connection with an inner product, you can always assume it is this one. Norm of f is square root of inner product of f with f. And the proof that this is a norm is mostly straightforward. Think about the positivity and the definiteness and scalar multiplication. The only thing that you really need to check with some difficulty is the triangle inequality, and I outline a proof of that in the notes based on the celebrated Cauchy-Schwarz inequality. And we should also note that if the inner product is only semi-definite, then the mapping of f to square root of inner product of f with f is only a semi-norm. Not every norm on a vector space is induced by an inner product in this sense, but at least two of our favorites are. So remember, if I have a vector x in Cn, then the 2 norm of x is in fact the square root of the dot product of x with x. And if I have a function f in the continuous functions on a to b into the complex plane, then the L2 norm on f, as we met in the previous video, is the square root of the L2 inner product of f with f. And so whenever you have a norm induced by an inner product, you can often do some calculations with that norm, say squaring the norm, to turn it back into an inner product, and then you can possibly learn some more interesting things about that norm.